friend recently told me about the advent of TypeScript challenges, and you know I love a good TypeScript challenge, so we're going to take a look at this today. This is the advent of TypeScript page. I'll have a link for this down in the description below. I haven't looked at any of these. I'm going into this completely blind. I thought it'd be fun if I kind of did this live, if you will, with you guys. The only thing I've looked at is if you hit the About section here, they mention that you might find the TypeScript playground useful in this, so I've got the playground locked and loaded over here, ready to go. Now, we'll see how many of these we can get through. On the day I'm recording this is, of course, the 16th because there are 16 available here. And so we'll see how many we can get through. I'm going to try and keep this video mostly unedited, I think, so you can at least see what my process is. So let's go ahead and get started. Day 1. Here we go. So all Santa needs to do is update the Santa's favorite cookies type to accept either of his favorite cookies. Can you help? Yes, this should be pretty simple. I think we just want this to be a union of our two strings here. So let's go ahead and write gingerbread or chocolate chip. Of course, these are both strings. We could have just said this is a string, but that wouldn't support only these two. In fact, let's see how good the type checks here are. If we write just string instead, and let's comment out the rest, yeah, we can see our tests are not actually passing here. Very good. So looks like we get a bit of a softball here to get us started. We get a green check, no red squigglies. Cool. Day 1 complete. At this rate, we'll be done in no time. And let's do day number 2. Okay, I don't think we need to read the whole story here. Let's jump to here. Take a look at the cookie inventory variable in the tests. That's right here. Your goal is to update the cookie survey input so that it will return a union of all the names of the various different cookies. Okay, so a union of all of these various cookies. That makes sense. Do we have access to these types up here? I don't know. Because what we could do, we could say key of, type of, cookie inventory. Oh, nice. We do have access to those variables. Cool. So now if we look at this, we can see we have chocolate, sugar, gingerbread, peanut butter, snickerdoodle, which are, of course, the keys that we have here. Oh, but actually, I think we have this a little bit backwards because you can see what's actually going on here is cookie survey input is actually supposed to take a type, and we need to get the keys of that. Okay, cool. So that's a small change for us. We can take some type, and then we just want to return the key of that type. Key of T is the right way to grab all the keys off of a T. All right, let's go ahead and submit that one. And day 3. All right, there's a gift wrapper type to help keep the wrapping process organized, but it needs something. It needs some way to be parameterized. What we have so far is a nice generic wink wink starting point. Okay, cool, nice hint. But it needs some way to provide specific values for present, from, and to at the type layer. Okay, cool. So you can see right here, we have gift wrapper, which needs car, which presumably is present, from, which is Santa, and then trash here, which is presumably the name of our to. So we can pretty easily take a present and a from and a to. Of course, you can use more than just single letters here. We could actually write these type names out. So for example, we could call that from and to. I usually stick to the convention of just one letter. I think what we want to do here is probably just plop these right in like this. So, and that's our test passing. Day 4, here we come. I'm going to skip to the bottom here. Today's task is to craft a type present delivery list that takes an object type as an input. Okay, so we know it's a generic, and then replaces the value at each property with an address. Interesting. We don't know in advance what properties will be provided, which is why it needs to be a generic type. So we need to replace the values at each property with an address. So present delivery list is going to take some T, and we need to replace all the properties of T with an address. That's an interesting thing. Okay, so what we need here is a mapped type. So we're going to map, so we're going to create an object here, and the key for this object is going to be the mapping piece, the iteration piece. So we're going to say K is key, I think the syntax is K in key of T. And then we're saying we want that to be an address at each spot. So we just loop over all of the Ks. So we loop over all the keys of T, right? T is the object we get in, and we're going to replace, so for the key on this side, the value, of course, we could put the actual value of this thing in place, right? If we did T at K, that would get us the value of whatever that property is, and we're essentially duplicating the type T. But instead, we're going to put in address, so we're going to replace everything with the type of address. And our tests are passing. I love this. Okay, We are flying through these. Day 5, normally the elves get lists like this, good list and bad list with lists of names, then copy and paste the values into a TypeScript type to provide to Santa like this. So Santa's list is, that looks like a single list though. Okay, but there's a problem. There's one elf on the team, Frymagian, that constantly reminds the others of how incredible his Vim skills are. Yes. So he has always done it in years past. However, this year, Frymagian got one of those MacBook Pros without the escape key, and his Vim speed is dramatically reduced. My tip for him is JK as a alias, to alias escape to that. I actually did it at the operating system level, I think, in my machine, because my keyboard right here does not actually have, let me unplug it, does not have an escape key. So, yeah. All right. So, Frymagian, I know where you're coming from, but let's see. Let's implement Santa's list such that it can be passed the types for bad list and good list, and it will return a TypeScript tuple with the values of both lists combined. Okay, so that is the case. That is what we're trying to do here, combine both lists. Okay, fine. So we take a generic here. The generic is going to be bad list and good list. And then I think what we just need to do is spread those. So we can do bad list, ... good list. However, as you can see, we do have a problem in our TypeScript here. Rest element type must be an array. And these are not arrays right now. So, and nothing says bad list has to be an array. So what we can do is say this extends unknown array, and the same for good list. Extends unknown array. There we go. Ooh, now we're not actually passing the types yet. We have a type error down here. So read only, okay, this is good. Read only Tommy and Trash does not satisfy the constraint unknown array. Yes, it's not read only. Okay, so we need to actually make this a read only array. So maybe a better way to do this would be to use the read only array generic instead of just using the square bracket syntax. So we can say read only array and square brackets be gone, and instead use angle brackets. All right, there we go. We have passing tests. On to day 6 actually. Okay, filtering the children part 1. The first parameter of filter children by is just a union of all the children's naughty and nice status. The second parameter, okay, so we have 2 parameters here we know. The first one is the status, and the second one is the thing we want to exclude from the final resulting type. Okay, I don't have a good word for that. We'll just call it T. Take a look at the test and you'll see some examples. Yeah. No, the engineering team managed a triple check, blah, blah, blah. Okay, fine. So filter children by, we have naughty, or we have nice, nice, nice. So a union of these values. And then naughty is the result. And what we expect this to equal is just the word nice. Okay, so we're removing naughty from this list. Same thing is here if we have nice, naughty, naughty, and then we end up with nice because we're removing naughty. And then here's a different type example. We have string, number, and a function. And if we remove function, we have string and number. Okay, so this is kind of, I guess, kind of like a version of omit. Okay, so this is an interesting one. We have to remove elements from a union. This is a little trickier. I think this may have to do with, what is that term? Distribution, I think. I know I wrote a blog post upon this a while ago. Distributive conditional types. I think that's what this is about. Yes, this is a blog post I wrote where, yeah, we need to filter a union essentially. Okay, let's give this a try. I think this is what we need to do. So I think what we want to do is we want to say if status extends T, then we get never, because we're trying to filter out T. Otherwise, status. And I have my ternary syntax wrong. Let's do this. Okay, cool. That works. So let me kind of explain what's going on here. Status is a union. T is some other type. It could also be a union, right? When you have a generic parameter and then also a conditional type, the combination of those two things triggers a iteration behavior essentially in TypeScript. And maybe I'll link to this post here that I wrote a while ago as a example where you can find more information. But essentially what's happening is we're iterating over every value in status. Because remember status, and when I say value, it's really a type, but every type in the type union that is status. And individually we're seeing, does that extend the type of T? And if the answer is yes, it does, then this is a true statement. And if the answer is false, of course, then it's false, and we would get status in this case. But then the key thing to keep in mind is that once that comparison happens across every type in the type union, you get a new type union out at the end, and then the nevers are filtered out, and then you end up with just the values in status that do extend T. So what's going on here is we're comparing nice, nice, and nice to naughty, and the end result is just nice. Now you might wonder, why is it not nice, nice, nice? Well, what we can do is if we copy this type up here, and let's call this type nice. When you have multiple values in a union that are the same value, they kind of just collapse, right? Because it's the same thing. Nice or nice is just nice. And so even just looking at this straight on, you can see that TypeScript recognizes this is a union that really only has one value. All right, so that is, I don't remember what day we're on, day number 6. Excellent type challenge. I love that one. Now I think that said that was a part 1. So let's take a look at day 2 here, which is, yes, filtering the children part 2. Start by identifying the inputs for our append good type. Ask yourself if there should be any generic type constraints on the inputs. There may not need to be, at least not right away. Then try to set up a scaffold that will at least return the same values for each property. Your next step is to transform the property somehow. Okay, so let's take a look at what we need to do here. We have a well-behaved list, which is a bunch of kids' names as the keys, and then this address object as the values. And we're going to do append good. Ooh, we're mapping the names like this. We're changing their property names. Nice. So where the key becomes good Tommy, good Timmy, good Trash, good Candace. I love that. Yes, changing keys like this is a really fun challenge. And we do this with a map type. Now, it said we may not need a generic type, but I'm gonna say that's a bit of a red herring, because we definitely do need that. We need to be able to map over the type. So we already looked at mapping a type a moment ago. Remember, we had key in, we don't need type of, we could just say key of T. And then in that case, we had address. But in this case, I think we just want T of K, because we want to use the same value, right? We kind of want the same thing in and out. And so what we can see if we do this is our well-behaved list here. If we hover over this type, you can see it's the exact same type that we put in. We haven't actually changed any of the key names yet. And so, of course, our tests are failing. However, what we can do is say as here, and this is not exactly as in the way that we use it in other places in TypeScript, in the way that you should probably avoid using it. What we're doing here is we're actually replacing the key with another key. So we're saying the key, or whatever value would go here, right? We want that to be represented as something else. And we can use a template literal string, and we can say good underscore K. And now we're prefixing good underscore to the beginning of K. So we have a problem here where K is not assignable to the type string, number, big int, boolean, null, or undefined. So what this means is that union that we just read there, string, number, big int, boolean, null, or undefined, those are the types that you can interpolate into a template literal type like this, right? Those are the things we can plug in here. However, K doesn't match that type. And if we go down to, and if we go to the very last line of this, it tells you exactly what the problem is here. Symbols can be keys, and symbols are not in this list. Symbols can't be interpolated into strings. So this is fairly straightforward. We basically can't support symbol keys. And I don't see any symbol keys in this. I think, honestly, the simplest way to do this is with a conditional type, where we can say if K extends symbol, then I guess let's just say never. Otherwise, this. Does that do what we want it to do? Not exactly. It still says this could be a symbol. Is that not the right way to determine if K is a symbol? I guess another way to do this, because we can see in our example specifically that these are all strings, we could say if K, oh, maybe it's because symbol was uppercase. Let me try lowercasing symbol. Does that do what I want? Strange. Okay, well, let's do this backwards. We know everything here is going to be a string, so let's just do string and never. Maybe that is not the most future-proof, but it does pass these tests, which is the main thing I care about right now. And we could, if we expected other things, we could just say, put that whole union in here, right? String, number, big int, all of the things that we could support as a key. I'm surprised we can't exclude symbol instead of having to check against everything else, but that's good enough for now. back to our type adventures here and choose day 8. Almost halfway through. All right, filtering part 3. We have not a lot of instructions here. Off to the tests to see how this actually works. Okay, that's fine. So, look at this. Now we have naughty, good, and we need to remove the naughty children. So we have to remove the 3 keys that start with the word naughty. Okay, this is nice. We can start with basically where we left off in the previous example. Now, remember, we just talked about how we can try and exclude symbol, and I didn't go into it too much, but what we did there to exclude symbol is we said if it wasn't a string, is what we ended up using, then we just use never as the key. And keys, and in an object where a key is a type of never, we just don't have that key at all. So if we need to exclude keys, we can do it by saying the key should be never. So as you can guess, this is another key renaming example. And what we can do here is, again, a conditional test. So what we want to say is key extends, and our template literal string is going to be good underscore, and then we can infer something that comes after good. And if that's the case, then let's use K. Otherwise, let's use never. Okay, I think that is going to be my start. So if we look at our well-behaved list here, we can see we do just have good Timmy, and we've successfully filtered the rest, and this test should pass. This test is passing. However, it looks like there's another test that's not passing. Interesting. Don't cheat is this one, and naughty play fair should be the one that's excluded. Instead, okay, I've done this backwards. Really, I've said, okay, yeah. Now, and the type name here should give this away. Remove naughty children is the name of this type, which is a prompt. What we've actually done is we've included the good children. So we need to kind of reverse this, right? We need to actually look to match naughty underscore. And if it does match, then we want to say never. Otherwise, let's say K. Hey, there we go. Green check mark, passing tests. Love it. Let's jump into day 9. Ooh, reverse. This should be fun. Reverse is going to be trickier. So we need to write a reverse type. Yes. Basically, it takes a string and we need to reverse it. What we need to do to reverse a string, I know that we need to recurse over the string, I think. We kind of did this a little bit in, I think, my last video, where we were solving the first part of the advent of code with TypeScript. Let's see what we can do here. Let's see what I can do from memory before we start looking stuff up. So we have our string, right? And if we return our string, obviously, that's just wrong. We were returning the string instead of reversing it. So I think, though, what we want to do is match the first letter of the string using type literals, right? So can we, does this extend something where we can infer a char, and then we can infer the rest? And actually we need to call that rest. I think this might work. I think this will just match a single character, and then this will, actually, I think we can do ... Is that how that works? No. What am I thinking of? Let's try that for a second. Actually, let's just return char and rest in this case. Otherwise, if nothing matches, we return never. So in this case, what do we get? Oh, nice. Okay, this is exactly what I was hoping for. We get R, and then we get the rest of the word matched. Perfect. What we want to do then is, I think, reverse needs to take a second generic, which is an accumulator, which maybe defaults to an empty string. What we need to do is append this letter that we've popped off, or I guess I should say, no, append it to the accumulator and run this again for the remaining characters, right? So we know that what we want to put in here is reverse with rest and accumulator. What will happen, I guess, is that in the case where we can't infer a rest, then really instead of never, what we want to do is return the accumulator, right? And if we think about this for just a second, actually, let's replace this with our char and our rest, right? And let's just create a new type here. Okay, so if we look at this, you can see we get A and then NDREW, right? We're matching here. Let's say we were in a case where we only had a string of one letter. So we shouldn't be able to infer both a character and a bunch of other characters after it. So in that case, we should just get our accumulator, which is, maybe we can just call this ACK for the moment so that we can see what's happening. If we hit X, oh, we actually do get that to work. That's interesting. So we need to then check to see if reverse, but reverse is always going to be an empty string. Maybe we can ignore that problem for the moment. So what we can do is say we want to reverse and we want to use rest as our string. And then for our accumulator, let's create a new string here. We're going to start with the accumulator as it currently exists, and we're going to put our character at the end of it. Accumulator may not be a string. That's fine. We can do accumulator extends string. And now if we look at X here, oh yeah, let me actually remove that. And now if we look at X here, okay, we do get Andrew. That works. I think, oh, you know the case that I wasn't thinking about? Okay, let's just throw ACK back in here. Obviously, you can see if we have characters, we get ACK at the beginning. But if we pass an empty string, that's the situation we want to talk about. We just get ACK, right? What's happening is, yes, if there's one character, you can infer a character and an empty string. If there's no characters, you can't infer two pieces. And that's where we get just our accumulator. So what we should see if we take that out is, I think now, are our tests passing? Why are our tests not passing? What is this equal? Hold on. Did I not actually reverse Andrew? I thought I saw that reversed. Oh no, it's the same way. Oh, duh. I put the character on the wrong side of the accumulator. Okay, that's a dumb mistake, but there we go. Okay, so now we have Andrew backwards, and now all of our tests are passing. Okay, excellent. So that is our reverse string type. Back to our types. What are we up to? We're up to day 10. We just have to write a street suffix. This will take two generic arguments. The first is the street. The second is the suffix we're testing against. If the street ends with that suffix, then the type should return true, otherwise false. Okay, that's pretty simple. Does it end? Ooh, I say that's pretty simple. However, let's see. I think the fact that we have to match against the end of the string might be challenging. So we have the string that we're matching against, or actually let's call it the main type and the suffix is the way we're going to call this. So we just need to return true or false. How? I don't think we can anchor to the end of a string. Let's try this. We'll try the simple way first. I have an idea for a more complex way, but I hope we don't need that. So let's say, does T extend some string where we can infer something at the beginning, but then it ends with the S? And let's say that S does have to extend a string. Actually, both of these do. Extends a string, right? Both of these have to extend string. Okay, so if it does, return true, otherwise false. Does that work? Oh, awesome. That does work. Sweet. For some reason, I thought we may have trouble anchoring to the end of the string, but I guess this does match the entire string, so that does make sense. The backup way that I was thinking was, I know, as we've already seen, you can match to the front of the string. And so in that case, I thought maybe we just have to reverse both strings and do that comparison so that the suffix that we want is actually a prefix. But this works, so we are good to go. Day 11. So Santa's list protector takes in an arbitrary type as an input and modifies that type to be read-only. The trick here is that it must also work with nested objects. Ooh, we are getting closer to the limits of my TypeScript knowledge, I think. But, so I know we can, I think we can, okay, I have an idea for how we can do this. Let's see if we can do this at least for the top level. So I think we have a mapped type here, right? We want to take some type T and do a recursive read-only operation to it. So we need to operate on every key. So we have, as we've seen before, K in key of T. And of course the type needs to be the same, but we need it to be read-only. So I think we can like wrap it like that. Now this is not recursive, so let's actually type this, test this. And then what we get out here, if we look at X, is the Boolean becomes read-only. I don't understand quite why the other ones don't. Let's look at the object we get out here. It'd be nice if this would tell me like which properties aren't read-only. Oh, good. Here we go. Okay. So the string is not read-only. this object is just read-only at the top level, but we haven't recursed into it. So we do care about like whether or not, what do we care about? Like whether or not whether or not this thing has fields of its own. So I guess what we can do here is we can say if t of k, can I just say like extends object? If that's the case, then we want to recurse through this. We want to say Santa's list protector for t of k, otherwise just t of k. It's kind of what I'm thinking here, right? So we recurse through it, and maybe I need to move this read only at the top level. No, I can't move it down a level. But maybe this doesn't work. There's also a thing where you can do like, oh wait, I can do like read only like that, can't I? Maybe that's the better way to do this. We're saying the property is read only. If we do that, let's see what we have here for x. I would say that is right. Yes, that I think is the type we want. Yeah, I think this looks better. So the problem, yeah, here, oh, interesting, because a function, of course, is an object. So that is what's matching there. Interesting. How could we do that? So maybe it's not just does it extend object. I guess it's because a function is considered an object. I wonder if we can do a bit of maybe we can manually, I don't know that this is going to be completely foolproof, but let's say function. If it's a function, then this is just t of k. Otherwise, if t of k extends object, then do that. Otherwise that. I don't love it. Oh, hold on. That works. So we just needed to take care of functions specifically? Interesting. I would be interested to hear from you guys if you think there's a cleaner way to do this. I do like that this works. I think it makes sense that we need to treat functions a little bit differently from objects, and there's not really a great way, I think, in TypeScript to just say, hey, is this a thing with, see, a thing with keys, everything in TypeScript, everything in JavaScript is an object. And so does this thing have keys that I could iterate over? Is maybe not a great way to handle this. Maybe what I care about more is like, is this a primitive value? That's actually, let's just try that first. Because I could create a type here that is, I call primitive. For this example, we can keep this pretty straightforward because we got like number, strings, booleans, and then functions. So let's just say, is this a string? Is it a number? Is it a boolean? I know there's other ones, there's other primitives that we would maybe want to include, like big int. I don't know about symbol. I guess it's a primitive, but we don't have any here, so let's ignore that. And then let's just say function, or can I say, I guess I can say function this way. I know like it's generally you don't do that, but because we're matching it here, that's okay, I think. So we could do this, and then what we can say is, if this extends a primitive, then do just t of k, otherwise recurse. Does that, okay, hey look, that's a little bit cleaner. I actually like that. I think that kind of declares our intentions a little more cleanly. So there we go. We have passing tests once again. I like it. I like that much better. Nested conditionals. That looked a little bit dirty. All right, where are we? Day 12. Find Santa. Ooh, emojis. This is going to be fun. Find Santa is a type that takes a tuple as its only argument and returns the index where Santa is located. Oh, the index. That's fun. So the thing with the tuple is, I think, we can map over it just like we do with an object, and the keys are actually numbers. Let's do a quick test to see if that's true. Let's not limit t just yet. We'll say k and key of t, and if we just return k for the moment, what I think we'll find is if we look at actual test here, yes, 0, 1, 2, 3, right? We get the index numbers of the elements in our list. And we expect 0 because Santa's in the first one. As we map though, we need to figure out where Santa is, and if this is a Santa, then we need to, okay, so here's my idea. Sorry, I know I kind of interrupted myself mid-sentence there. Let me show you something. So this is a good start actually, I think, right? Where we have 0, 1, 2, 3, because we have all of our indexes there. But notice that it's still a tuple. Now, if we do number at the end of this type, it's going to complain that number cannot be used to index type key of t. But I think it could if we said that t extends, is it a read-only array? of unknown. Actually, we know in this case these are all strings. So let's just, actually, it doesn't really matter. Let's say unknown because it doesn't matter. Nice. Okay, that works fine. So now, if we look at test 0, 1 here, notice we have 0, 1, 2, 3, but this time they are a union instead. So what we've done when we index on number, we can say, basically, I care about this type at number. Indexing into a array like this with a key of number instead of a key of like 0, 1, 2, 3 looks a little weird, I know. But remember, this is all in type land. So if I said specifically use the index 0, what I'm saying is find all the keys that have where their index has a type that is narrow enough to be just the number 0. And so when we say number, we're saying get me the type that represents all of the values where the index is a number, which is all of them. And so we get a union of all of those types, right? We can see we get 0, 1, 2, 3. Now, you might already know where I'm going with this because we've already talked about when you have a union and some of its values are never, those are just filtered out of the union, right? Because what does that even mean? So what we want to do now is figure out which values at these keys have a value of Santa emoji. So what we can do is rename these. We can say as, and we can say if K extends Santa emoji, then we can just use K. Otherwise, we can use never. All right. What is up now? Let's see. Number cannot be used to index the type. Okay, fine. What? We can't use the key as the key? Okay, I'm sorry. I've confused two different things here. Here's what's going on. We can't use number because now this is we're basically mapping this tuple into an object. Is this the wrong way to do this? I think maybe I want to do this condition on the other side. Wait, let's put this condition here where we can say if T of K extends Santa, use K, but let's not do that. Otherwise, never. And then number in there. I feel like that's kind of closer to what we want. That is 0. Okay, nice. Oh, that is the string 0, but we want the number 0. Okay, that's fine. That is one more conditional away. So what we can do now is we can add another condition in here. We can say if K extends, and we want to infer N extends number. I was kind of discovering that as we went along, so let's just start from the beginning. We have find Santa here. It takes a read-only array of values. Doesn't matter what the values are. We're going to loop over everything in this tuple. And if the value at that place is a Santa emoji, then we're going to return some specific type. Otherwise, we're going to return never. Now, what is the specific type we're going to return? Well, we're going to check to see if K extends template literal type, where we're matching we're inferring some value N as long as it extends a number, right? So we're saying, is K essentially a string that is a number that we can parse as a number? And this is essentially doing a parse int on N. And if we can infer a number out of that, then N is a type number and we can return that number, otherwise never. And now you can see all of our tests are passing. So we actually return 0 in the case where Santa's at the beginning, or we return never in the case where there is no Santa in the forest at all. All right. That was a fun one. I'm honestly having a blast. I hope this is a valuable video for you guys. I realize I'm kind of just speeding through this because I'm curious to see. Honestly, I don't know that an hour-long video is that useful to people. So, but if it is, that's great. Let's see how this works now. Okay, count the days. First argument is the beginning of the count, inclusive. Second is the last of the count, also inclusive. It should return a union of numbers representing the remaining days. Oh. Okay, interesting. So we take a day counter, it takes a 1 and a 12, and we have to return a union of days 1 through 12. Interesting. Okay, so we're gonna call this start and end. I don't love E for some reason. Let's do first and last. So what do we have to do? We have to do number comparisons. I'm gonna be honest, I feel like I am hitting the limit of my TypeScript knowledge here. How can we compare numbers? Well, okay, here's what I know we can do. We know that we can get a union of indices from an array. So if we can get an array with, it would have to be 13 items, we can get the indices and then we can, filter out 0. That feels more attainable. So what if we create an array with 13 items in it? Let's first just check to see if that's a thing that can happen. So if we create an array type here that has any, and then if we get type indices of A, where A extends a read-only array of unknown, then what we can do is simply map over it for K in key of A. Let's return K, and we get the number. And then if we do type X, we can do indices of A. We should get 0 to 3, right? 0, 1, 2, 3, except those are not numbers yet. So we can do if it extends, infer n extends number, then n, otherwise never. And now we get 0, 1, 2, 3. Perfect. And then can we do extends 0, never. A better way to do this would be type filter. Oh wait, we can just use emit for this, can't we? So let's just wrap all of this in an emit. And so now, ooh, that's not exactly what we want. Is exclude the one we want? I'll be honest, I always get confused between exclude and emit. There we go, exclude is what we want. Phew. Okay, so we know that if we have an array of 4 items, we can get the indices 0 to 3. And then we can omit 0. So that feels like a good start here. Now we just need to create an array. The easiest way to do it, I think, is going to be to add elements to an array until it becomes the right length. So let's say, and this is again something we did in the last video, isn't it? So let's create a type called length of, and we're going to take an n that extends number, and then we're going to take an accumulator that extends a read-only array of unknown that defaults to an empty array, right? If the accumulator extends an object that has a length of n, return the accumulator. If the accumulator extends an object that has a length of n, so if this array already has a length of n, then we can just return the accumulator. Otherwise, we do length of, oh, we got to do n minus 1. That's, we got to subtract. Oh, no, we don't. No, we don't at all. Because we're adding this up. So n is not, we're not adding n, we're adding up to n. So we can do n, and then we can do ... acc and add an unknown to that. Essentially what we're doing is we're saying, this doesn't work if you start us off with an array that's greater than n, but we're not going to do that. So if we have the number of elements we need, return that, otherwise add a new one. So we're spreading the existing list and we're adding a new one. Okay, so I think with these in place, we can probably solve this type challenge. So we can get our day counter and we can get the indices of length of, now, oh, there's an interesting problem here where like we need to be able to exclude. So in both of these cases, we're starting at 1, right? In both of the test cases here. But theoretically, you might want to be able to start at a number greater than 1. So let's ignore that for now, and then let's talk about that in a second. So we can just say length of L is the problem we need to solve. L does not have a constraint number, that's fine. So if we do type X equals day counter from 1 to 10, and hover over X here, what we see is we get 1 through 9. Ooh, fun. We are 1 number short. So we are missing the last number, so we kind of want a length plus 1. Ugh. What's an easy way to add 1 to this length? Now that we have length, I think we can create an add pretty simply. I wonder if I'm completely overdoing this though. Yeah, we can take like an A that extends number and a B that extends number, and this becomes we get a length of A, right, which length of A returns an array. So we can spread that, and then we can spread length of B, and we have this array, but then we need to like actually get the length of this. So let's just create one more utility type here that we're going to call length of an A that extends. I'm going to copy this type right here, some array that extends this, and we want to do this comparison right here, right? We want to say if A extends something that has a length of n, return n, otherwise never. And I think we want to infer this n. Yes. So then this, we can take the length of this array. Now I think we can take L here, oops, and let's add to L, we can add 1. And that doesn't work. What did we, let's double check that these things are actually working here, right? So if we say type X equals add 1 and 4, should equal 5, good. So that means length of and length is working just fine. What is going on here? Ooh, possibly infinite, interesting. I think we may have approached this a little bit too fast. This first one is passing. Actually, they're both passing. The reason this isn't passing, like these tests are passing, the reason this isn't is because of this. I mean, these shouldn't be, there's nothing recursive about add. Length does a single comparison, nothing recursive about length. Indices, nothing recursive there. Really, length of is the only recursive thing that we've got going on here. And how did adding L? Oh, hold on. Does not satisfy the constraint number. Yes, okay. Read the full errors, people. Don't assume you understand the problem. Type unknown is not assignable to type number. Yes, and that is because n, where is it? N here. We are inferring a length of n, but I think we want to say a length specifically that extends number. Well, that does work. However, and we didn't even get to the part about not excluding only 0, but excluding like f. I wonder if that's okay, let's try something here. Let's remove the exclude. Of course, that doesn't actually, that just breaks our tests here. I don't understand why this is why this thinks this is possibly infinite. This is a tricky one. Dimitri, you can see this prompt here is by Dimitri from the MITS YouTube channel. Definitely check that out. A lot of cool content over there. He's come up with these. He's also the friend who told me about this challenge. I think he may have stumped me with this one. This is a tricky one. I feel like I'm really, really close and I'm missing something obvious. Maybe, is there a better way to get a list of numbers than indexes off a tuple like this? Okay, well, let me point something else out here, right? We should change this, if we change this to f, right? To the first number, then what we actually get here is the list of numbers that we should exclude, right? If we look at this right now, you can see we do get 0 and 1. Why would we get 0 and 1? Because we're adding one element to, oh yeah, we're adding an element to the list. So if we take out the add, if we take out the add, and just f, which f needs to extend number as well. Then, well, obviously this test is failing. If we take out the add, then it doesn't think it's recursive. That's good to know. Okay, we're onto something here. So this is just a 0 right now. If we change it from f to L, you can see we get 0 to 11. So what we could do here is let's copy this and say where L extends f. Okay, let's actually move. We're gonna move this into another type as well, folks. Another one that we have seen before. Or is this just an exclude? I think it is just an exclude. So hold on there. Let's do exclude from L everything that is f. This is an interesting way to do this, right? We take the indices of the length of L and remove the indices of the length of f. And that way we're removing all indices from f downwards. If we look at what this type shows us right now, nice. We have 1 to 11. So we're missing a single digit. So the problem here is really just with our add, because here with L, what we need to do is our add to L, we need to add 1 to L. If we do that, notice these tests are passing now, but we get this deep and possibly infinite type instantiation. Is there a better way to add? We just need to add a single thing here. This is kind of frustrating. Okay, I wonder if there's a way to do this recursively, where we start with f and add an item to it and create this accumulator array. Let's give that a try. Let's comment this out, and we're gonna try a very different approach to this. We're gonna need to take something else here, which is an accumulator, which extends a read-only array of numbers, which starts as an empty array. We need to, okay. So if f extends L, if the number that we're adding is the same as the last number, then let's just return accumulator, right? This is gonna be our kind of exit for recursion. Otherwise, we need to recurse here. We have day counter, And we need, so let me uncomment add here. We're going to add F. We're going to add 1 to F. L will still be L. And the accumulator is what needs to change, right? The accumulator, we need to do our current accumulator plus F. Where does this get us? This gets us close. This gets us 1 to 11. That's not bad. That's not bad. That's pretty close. Because then what we can do is just, we can create another type here that takes our tuple to our array. So that's good. The problem again that we get here is our list now has 1 to 11. Why does it not have 12? Because in the case where F extends L, right, where F is 12, we don't do anything, but we need to do one more, right? We need to add one more time. So let's just return it like that. And in that case, if we look at this now, hey, look at that. We have 1 to 12. 1 to 12. Love that. Okay. So now, and that's seems simpler anyway, right? And now let's create a type here that we call toUnion, and it's going to take our read-only array of something. Let's change this to just A. Let's change number here to unknown. So what we need to do is map over the tuple. We can say for key, in key of A, we want to provide A at K, and then we want to take the number of that. And that should do it. And so now we're going to rename day counter to call this range, which is really what it is, a range utility. There's already a range type in here. Okay, we're going to call this range 2 because I am getting close to being brain fried. Let's copy our day counter one more time. And we're going to say this is toUnion on range 2 from F to L. Oh, look at that. Look at that. Look at that. Our tests are now passing. Amazing. Amazing. We've completed day 13. Oh boy. Okay. Love that. That was thrilling. Okay. We are, I guess there's 25 days, so we are just over halfway through, and the next set are not going to be any easier. I'm going to call it there for this video. We've already been recording for just over an hour. I know there's a few things I'm going to clip out, so you guys hopefully will get something maybe around 50 minutes. I don't know. We'll see what this looks like. But this was a ton of fun. Thank you. I didn't see if they were all by Dimitri, but maybe they are. Does this say anything more in the about section here? But anyway, definitely check this out. Definitely do check out Michigan TypeScript as well, because that's a pretty cool channel with a lot of fun stuff on there. I will be back maybe to do more of these in the future. I promise. Not going to look at any of them until that happens. And yeah, thank you guys so much for watching. I'll see you in the next one.